All right, well, good evening, everyone, and welcome to the May virtual Meet the Astronomer lecture with Vanderbilt Dyer Observatory. I'm Dr. Billy Teets, and I'm going to be your host and your presenter tonight. So I'd like to welcome you all, and thank you for joining us this evening. Behind the scenes, we've got two of my colleagues, Brian Smokler and Helen Morissette, who are going to be monitoring the chat, making sure that our stream is getting out. So I want to thank them first and foremost. Since you're watching on YouTube, there should be a chat button over on the side, and we're going to be monitoring the chat. So as we go through the presentation tonight, if anyone has any questions about the topics that we're going to be covering, please put those questions in the chat. We're going to hold the Q&A session until the end, but as a question comes to mind, go ahead and put it in that chat, and we're going to keep a record of those, and we're going to try to get to as many of those questions at the end as we can. So remember, there are no silly questions. So if you got one, put it in there because we want to hear them. Let me share my screen right quick. In fact, I'm just going to go ahead and share it for the rest of our presentation this evening. So before we get started, I just wanted to highlight a couple of things that you might want to check out on the Dyer Observatory homepage, which is dyer.vanderbilt.edu. Dyer Observatory is still closed to the public, but we're hopeful that we will soon be reopening. We will post any details that we have about our reopening once we get those, and those will be posted onto our website, and they will also be posted onto our social media. Actually, let me scooch over to that right quick. So follow us on our social media. We've got Instagram, we've got Facebook, we've got Twitter, we've got a little bit of everything, okay? So any details that we have, we're gonna let you all know as soon as we have those and on these pages in social media, so be sure to check those out. Also on our homepage, we've got a couple of things that you might be interested in downloading. We've got a couple of star charts. Last Saturday was our virtual star party for May. We had a great program, even though we were clouded out. But we set up these star charts to where folks could take them, see them on like a smart device, excuse me, or print them out and go out and learn what's up in the night sky. So we've got the really nice colorful version that you'll see on the left there. That's great for a computer or a phone or a tablet. But if you'd like a paper copy, we've made one that's much more printer friendly and a lot less hard, or a lot more easier on the ink there. So that's what you see on the right side there. And then also we've got our May celestial calendar that Dyer's own Alex Rockefeller put together. It is crammed full of lots of graphics, information. You're going to learn a lot if you download this and start studying it, because there are dates that show specific things happening in the sky, whether it's the space station going over or seeing a conjunction of planets. There's listings of this day in history, so a lot of information on there, and we'll be seeing June's calendar coming out here pretty soon. It's hard to believe that we're already almost halfway through the year. So those are all on the Dyer Observatory homepage. We also have a link to our playlist for previous lectures, previous star parties, and lots of other things. And again, that link is on the Dyer homepage as well. So got our little announcements out of the way there. So let's move on into the topic for this evening, which you probably guessed is about lunar eclipses. So in this talk, we're going to be covering a few different things, okay? So I'm going to start with a little bit of background on the moon, not necessarily pertaining to eclipses, but just getting you some background information on the moon, things that everybody can appreciate and honestly, I think should know, okay? After that, we're going to go into the how and why of lunar eclipses. We'll mention solar eclipses a little bit, but we won't really go into a lot of detail on those. We're going to focus on the lunar eclipses because we have some upcoming lunar eclipses. In fact, in 2 days, Nashville will get the tail, well, not the tail end. We'll see a little bit of the May 26th eclipse, but we won't get to see the entire thing. But we have another one coming up this year that we're going to talk about as well. Okay. So that's the basic idea for tonight. So let's start with a little bit of background. And again, if you have questions, don't hesitate to post those into the chat. All right. I like to start out by talking about just how big our natural satellite is. So here we have an illustration of the Earth. Let's imagine we had an Earth globe sitting on a table like we see here. The little circle that you see under it, that's basically showing you the diameter of the Earth. Now I want to ask you, how big would our moon be if you compared it to this Earth? So if I was going to make an Earth-Moon system, and I want to make them lifelike, so the moon's the right size compared to the Earth, how big do you think it would be? So I'll give you all a couple of moments to think about that. Now don't look it up. I want you all to guess here. But if you're with friends and family watching this, maybe you all can have a discussion, or you can see who's going to be right. But I'll give you a couple moments to think about it. All right, everybody got their answer? All right, here we go. That's how big our moon would be. I would suspect that a lot of you may be amazed at how small it is, because when we look at our moon in the sky, it looks pretty large. And, it is a large object. It's about 2,200 miles wide, but it is notably smaller than our own planet. So our moon is around 1/4 of the diameter of our Earth. That means you could fit about 50 moons inside the same space that the Earth would take up. So you would think it would have about 1/50th of the mass of our planet, but in fact, it only has a little less than 2% of the mass of our planet. And that's because Earth has a big iron core. The moon, it's got a core, but it's not a substantial iron core like we have here on the Earth. In fact, the material that makes up the moon is thought to have come, or at least a lot of it, was thought to have come from an impact of an object hitting our Earth and basically stripping a bunch of the crust and some of the mantle of our planet completely off, and that went into orbit and coalesced to form our moon. So the outer parts of the Earth are lighter materials. The core is much heavier or much more massive, denser. So that's why we have less mass in our moon. But if you do the math, you find out that you weigh about 1/6 of what you would weigh, or you weigh 1/6 on the moon, what you would weigh here on the Earth. So anyway, a few numbers there. But now let's imagine we want to set up an accurate Earth-Moon system. So we've got our Earth, we got our moon. Let's imagine that our Earth is the size of a large marble, so maybe 1 inch in diameter, okay? And so with that scale, our moon would be about the size of a pea, okay? How far apart would I have to place those to make an accurate representation of the Earth-Moon system? So again, I'll give you all a few moments to discuss with friends, family, or just think to yourself. So again, our Earth is going to be about 1 inch in diameter, and the moon's about the size of a pea. All right, so 1 inch Earth, pea-sized moon, they would be about 30 inches apart. Okay, so I can't quite show it here. I have to back up just a little bit here, but about like that. So almost a meter wide. Believe it or not, that is the accurate scale of the Earth-Moon system. So here is a scale drawing showing that. So the moon on average is about 240,000 miles from us, but the moon is in an elliptical orbit around the Earth. And so as it goes around the Earth, it's changing its distance. Its closest point to the Earth, a point called perigee, is about 224,000 miles from our planet. Apogee, the farthest point from our planet, is about 251,000 miles. So our moon is varying its distance from the Earth all the time. So that does have an effect, and as we'll see, that will play a little bit of a role in eclipses as well. But in recent years, especially thanks to social media, we've really kind of heard more about this varying distance of the moon from our planet, because we have these things called supermoons. So when the moon is closer to the Earth, or near its closest point anyway, it's going to appear larger in our sky. Now, when it's much farther away, it's going to appear a little bit smaller. So when we have a full moon occurring around the time of perigee, or when the moon is near perigee, then we have our supermoon. And when it's near apogee, then we have our micromoon. So as you can see, there's not a humongous difference in the sizes of these full moons. Now, when we hear about these supermoons and you go outside, I know I have done this myself. I think, oh, wow, yeah, the moon definitely does look much brighter. And I think it's a little bit bigger. But really, that's just because I knew that it was a supermoon because I'd heard about it. Okay, so they're really not super, super brighter than a regular or an average full moon. They're not humongously bigger. You'd really have to make very fine measurements to be able to detect that difference. Okay. All right. Now, one thing that you'll notice in these pictures of our full moons, which by the way, May's full moon and all of the full moons, they tend to have these fun names. And those names vary by culture. And often there's a lot of different names for the same full moon of a month. This month's full moon is called the flower moon. And just so happens that this month's full moon is also a supermoon. If I'm not mistaken, it's the largest supermoon for 2021. And not only that, but it happens to coincide with a lunar eclipse coming up in just 2 days. Now, does that mean the supermoon is causing the lunar eclipse or the lunar eclipse is causing the supermoon? Doesn't mean that at all. It's just that they happen to coincide at the same time. Okay. In fact, the lunar eclipse we'll have after May's lunar eclipse will occur in November, and that will actually occur during a micromoon, but it's not always that way. Okay. But one thing I also want to point out here, we always see the same face of the moon from the Earth. If you go out tonight and look at the moon, you'll see the same areas that lit up that you'll see on other nights. We don't see the opposite side of the moon. So this view that we see here, this is what we call the near side of the moon, because that's the side of the moon that is facing the Earth. Okay. The opposite side of the moon, if this is the near side, the opposite side is the far side. It is not the dark side. And we're going to show why that is in just a little bit. But to do that, I'm going to use another program to simulate some views here. So this is a program called Stellarium. We've used it in a number of our presentations. We've used it during our virtual star parties. You can download it for free to your Windows or Mac computer. There's a mobile version. There's even a browser-based version, which doesn't have as many bells and whistles, but it's still really nice. And you don't have to install anything. You can just go to that website and you have a browser-based planetarium that will allow you to explore the night sky. But let me do a new screen share here. All right, so the view that we have here is the view from the Stellarium window. So what we're simulating here is the sky as it currently is over Nashville. Now you may notice that this doesn't look like Nashville, and that's because you can change the landscape if you want to. But the view that I have here is like if I was lying on, let's say, a raft in the middle of the ocean, and my head was pointing north, and my feet were to the south, and I'm just lying on my back looking straight up at the sky. This is essentially the view that I would have, okay? And I chose the ocean because we have a good, clear horizon, okay? In fact, we can even make the ocean go away if we wanted to see what the entire 360-degree sky looks like. But what we're going to do is take a look at the Earth and the Moon system from a different vantage point. So we're actually going to go over to this bright object in the sky that we call the sun. We're going to get a viewpoint of the Earth and the sun, or excuse me, the Earth and the Moon from the sun, okay? So now I'm going to have the program find the Earth for me. Alrighty, so it's switched on around, and now I'm going to zoom in, okay? So now we're starting to see two objects here, which, by the way, these little red lines, just ignore those. That's the program saying that it's selected that particular object and is displaying the information up here. Okay, so they're not satellites or anything like that. All right, we're going to continue zooming in here. All right, there we have our Earth and our Moon there. Now you may say, well, aren't they a little bit too close together? And in fact, we're not seeing them at their full distance. Okay, so what's happening here, since we're 2 days away from full moon, the moon is actually coming on around, and it's going to pass in behind the Earth here. Okay, so it would actually go, if we reverse time, we would see the moon moving on out this way. It would disappear off the screen, and then it would eventually come back in and move around this way. So we're just not seeing it. We have a perspective effect, essentially. Okay. Now, what I'm going to do is I'm going to instead select the moon. We're going to center in on that. And then I'm going to zoom in. So you could say, oh, wow, the sun. So remember, we're standing on the sun. Okay. You can say, oh, if I had my telescope on the sun would see the same moon that I see. Well, let's check this out a little bit more. If you notice down at the bottom of the screen here, there's the date right there, and there's the time. Now, what I'm going to do is speed up time significantly, okay? So I'm going to go ahead and start doing that. Let's see, so I think now every second is 1 day. What do you notice about the moon? The moon is rotating. The moon has to rotate in order to keep the same face or that same side towards the Earth. So we just passed the Earth again. So we just passed our new moon phase. And now the sun is seeing all of the far side of the moon. Okay, it looks a little bit different than the side we're accustomed to. You notice there aren't as many dark areas that are called Maria, so large impact sites, but there's lots of craters. But the other thing I want you to notice, do you see any pitch black areas on the moon? You don't. The far side of the moon, especially during new moon, is completely lit up in this case, okay? So during new moon, the far side, what a lot of people normally call the dark side, is actually completely lit up. In fact, there's only a few small areas on the moon that don't receive sunlight, and those are craters at the top and the bottom of the moon, at the poles. And because the moon isn't really tilted over much, those craters don't really get to see sunlight. But that's an incredibly tiny amount of the moon that doesn't see sunlight, okay? All right, so I'm gonna continue on. So now, let's see, we are about 1 day per second. So now the moon's coming on around. It's probably about the first quarter phase, and now the full moon phase. And we're seeing the near side of the moon, but now as the moon comes on around, we're starting to see the far side. So the moon's rotation on its axis, what we're seeing here, takes the same amount of time as it takes the moon to go around the Earth. And so as a result, it's able to keep that same face pointed towards our planet, okay? All right, so we're gonna come back to Stellarium in just a little bit here, because we're gonna do a few other things with it. But let's get back to our PowerPoint here. All right, so we saw that we see, one side of the moon. So how much of the moon's total surface, near side and far side, can we actually see? You may say it's 50%, but it's not quite. There's an effect called libration. And so here's the simulated phases of the moon, and there's several things I want you to notice. First of all, you notice the moon's kind of wobbling back and forth. That's because as it varies its distance from us, going from apogee to perigee, that change in distance also causes it to speed up and slow down as it goes around the Earth. But it stays rotating on its axis at the same rate. So sometimes that synchronization that allows it to keep that same face towards us gets a little bit out of whack. Sometimes the moon's moving a little bit too fast in its orbit. And so therefore, from our viewpoint, it's not rotating fast enough to quite keep that axis, or to keep that face, that same face pointed at us. Other times when it's farther away, it's moving a little bit too slow. And so therefore the moon's rotating a little bit too fast in order to keep that same face pointed towards the Earth. So that gives that wobbling motion. You'll also notice that it's, sometimes we can see down here a little bit farther behind. Other times we can see up here a little bit more. It's kind of like we're looking over and under the moon. And that's because the moon's orbit is tilted with respect to our orbit around the sun. So at certain times, we can essentially, it's kind of like the moon is kind of leaning over are leaning back a little bit. And so that allows us to see a little bit more of the bottom of it, and at other times a little bit more of the top of it. So when you add all of those effects together, over the course of, say, a year, you could see up to 59% of the moon's surface, okay? But at any one time, if I went outside right now and looked at a full moon, I would only be able to see 50%, okay? So there's a lot of motions that go on with the moon here. So I want to talk just a moment about moon phases. So we're not going to go into a lot of moon phases, but one thing I do want to address is a huge misconception among a lot of people. And I see this a lot in my astronomy classes. And this is one of the main things I try to really teach people. I say, you know, if you're going to learn anything out of an intro astronomy class, you should learn why the moon has phases. And unfortunately, there's a huge misconception that the phases of the moon are caused by the shadow of the Earth. So we're going to talk about why that cannot be, okay? So we have our sun over here, and we're essentially up above the Earth here. So we've flown up from the North Pole, and we're looking down on the Earth-Moon system, and we're also looking at the sun here. So sizes and distances aren't right, but we're not worried about that, okay? So what we've got here is the moon at 8 different positions. Now I want you to notice that at each of these positions, the half of the moon that is facing the sun is illuminated, just like the half of the Earth right now that is facing the sun is illuminated. So if you're on the side of the Earth that's facing the sun, you're on the day side. If you're on the side that's in darkness, you're on the night side, okay? So that's these 8 positions for the 8 different phases. So that's where the moon would be, of course, not the right distance. But the outer images here, that shows what we would see from the Earth at each of these different phases. So for example, at this position right here, this is what we would see in the sky. Over here at this phase, this is what we would see. So a lot of people think that the shadows of the Earth cause the moon phases. Well, if the sun is over on the right side of the view here, that means that the shadows are going to be streaming over to the left side of the view, okay? They're going to be behind these objects, all righty? So that means the shadow of the Earth is going to be coming over this way. Shadow of the moon is going to be coming over this way. So let's look at new moon. This is when the moon has come almost directly in between the Earth and the sun, and we're seeing the night side of it, okay? Because the far side is in full sunlight. So if the Earth is here and the shadow is over here, how could the shadow possibly cover up the moon when it's over on the right side here? The answer is it cannot, okay? And what's even more perplexing, if you have that misconception, is that we look at full moon. Well, if the shadow of the Earth is coming this way, at full moon, which is the phase of the moon where we see the entire near side lit up, we don't see any shadows on the moon typically. So the shadows do not cause the phases of the moon. What is the cause? Well, just keep in mind that whenever you have a sphere or a ball and it's got a light shining on, half of that ball is going to be lit up, just like we spoke about a minute ago. So as the moon is going around in its orbit, when we're over here, the half that's lit up, we can't see. But as it starts to come on around here, we're starting to see a little bit more and more of that lit side. And as it finally gets to where we're in between the light source, the sun over here, and the moon itself, we're seeing the same viewpoint as that bright sun, which is streaming out light and illuminating the moon. So again, it's just where the moon is in its orbit and how much of that lit side we can actually see. All right. All right. So now let's talk about some other things that we can see with the moon here. Now, as you saw in, the very first title slide, we had a very red moon. Now, if you go out to, if you have a good view of the eastern horizon and got clear skies and you see a full moon rising, you're going to see the moon looks much redder when it's near the horizon than when it gets high in the sky. But one thing you'll note is that that red color is very uniform, okay? This is not a lunar eclipse, okay? This is actually an effect of our atmosphere. So there's an effect called Rayleigh scattering where because of what our atmosphere is made of, when all colors of sunlight come through our atmosphere, the bluer colors get scattered quite a bit. They kind of bounce around all over the place. The red colors, they really don't bounce much. They aren't really affected, okay? But that blue light bouncing all around in the sky, that's what gives us our blue sky. It's not a reflection of the oceans, which is another misconception. It's because of the composition of our atmosphere. And that composition, that nitrogen and oxygen, will really affect how the blue light gets scattered around. But that red light, when it comes through pretty well. It doesn't get as hindered as much. It does get hindered some, but not quite as much. So everything appears redder when it's near the horizon. So this full moon that we see here, for somebody else, a quarter of the way around the globe, they would see the moon already high in the sky, and they would be seeing a very grayish white moon when I'm seeing this very red moon. So what's happening is the red, or all the colors of the light that are being reflected off of the moon. Remember, the moon is not glowing on its own. It's just reflecting sunlight. That light being reflected from the sun is coming through our atmosphere. The blue gets scattered around, and so it doesn't get to our eyes as well, but the redder colors do get to our eyes. And so the moon will appear very red, just like the sun appears very red when it's near the horizon, okay? Here's another good example. So here's a time lapse with multiple images of the moon overlapped. You can see that the closer the moon is to the horizon, down here, that it was much deeper red because the bluer light was scattered even more, and even some of the red light was scattered. And because we're looking through more and more atmosphere, the closer we are to the horizon, the more of that effect that we see, okay? So as the moon gets higher up, it starts to lose that color, and it also starts to seem like it's getting brighter, okay? But it's purely an effect of our atmosphere. And what we're actually seeing is an effect on our view of a white moon, okay? Which will be a little bit different when we talk about eclipses in just a second. Here's just kind of a demonstration of a similar effect. This isn't quite Rayleigh scattering, but it's a very similar effect. This is opalescent glass, and you'll notice that the glass, which is being illuminated by a white light source, it appears to be rather blue because as all those colors of light enter that glass, the blue gets scattered around more, and so it's not able to exit the glass, whereas the redder colors get through pretty well, and they're able to exit out back here. And so you see how the light that does come out has a very kind of reddish orange color to it. One thing I also want you to note, and this will come up a little bit later when we talk about eclipses, notice how there's kind of a bright spot right here. And that's because this round shape of this little opalescent glass ball is acting like a lens, and it's focusing a little bit of that light, okay, to make the spot brighter there. That'll be a key that we're going to talk about when we talk about eclipses, so keep that in mind. Speaking of, let's actually get to some eclipses now. The basics of an eclipse. We've got two broad categories. We've got our solar eclipses, which occur in the daytime. Those are the ones that you have to have eye protection for. Those occur at new moon, when the moon is coming in between the sun and the earth, and it's able to cast a shadow on the earth here. Now the lunar eclipses, those are kind of where we do a little switcheroo, where we have, instead of the moon coming in between the sun and the earth, we have the earth in between the sun and the moon and casting a shadow onto our moon. For each of these types of eclipses, you'll notice that there are some shadows. Now, this is like a cutaway of a shadow here, okay? So like we took a knife and we kind of sliced through the shadows. These shadows are actually cone-shaped, okay? So this inner shadow called the umbra, this is the darker inner shadow, that is surrounded entirely by a lighter outer shadow called the penumbra. So the bigger shadow has the bigger name, okay? Smaller shadow has the smaller name. If you're in the umbra of the earth, or if you happen to be in the umbra of the moon, then you will see the sun completely blocked out. If you're in the penumbra, then you only see part of the sun blocked out. So this will play a role in the types of eclipses that we can see. One thing I want you to notice here, and again, the sizes and distances are not scaled correctly here, but what I want you to notice is that the moon's umbra, the point where it actually touches Earth, where we could see a total eclipse, is pretty small. That's why you have to be in just the right path in order to see a total solar eclipse where the sun is completely blocked out by the moon. A lunar eclipse, though, notice how much bigger the shadow of the Earth is compared to the moon. So the moon, it's not going to have one little area covered. The entire moon can be covered during these types of eclipses. And because the moon has a large shadow to travel through, about the size of the Earth, where compared to the spot size that's about maybe 100 miles wide on the Earth, where we have to be to see a total eclipse of the sun, lunar eclipses, especially total lunar eclipses, will last much, much longer than a total solar eclipse. Okay? And you don't have to be in a special spot on the Earth like you do for a total solar eclipse to see totality. For the lunar eclipse, a total lunar eclipse, you just have to be on the side of the Earth that is facing the moon. So that makes lunar eclipses much easier to see. Okay. One other difference, lunar eclipses, you don't need any special protective eyewear. You can stare at those for as long as you want. It's just like looking at the full moon, except that the moon is dimmer. So it's even better than looking at a full moon. Not that the full moon will damage your eyes, just saying it's much more pleasing to the eye because it's not quite as bright. It's got some color to it. You see some changes going on. They're really spectacular if you get to see these lunar eclipses. Okay. So again, we have to have the moon over here, which means we are at a full phase for a lunar eclipse. We have to have a new moon in order to have the solar eclipse. Now, how often do we have those phases of the moon? Let you think about that for a moment. So we have to have the full moon for a lunar eclipse, new moon for a solar eclipse. How often do we have those phases? The answer is we have them every month. How often do we have a lunar or a solar eclipse? Is it every month? Is it maybe once every 2 months, once every 3 months, once a year? What do you guys think? I'll let you think about this for a moment. All right. So we don't have lunar or solar eclipses every month, even though we have these correct phases every month. We have these eclipses about once every 5.5 months. In fact, there is a window of time called an eclipse season in which we can have eclipses. And again, they occur about every 5.5 months. So let's talk about why that is. So here is a quick diagram. We have our Earth here. We have our moon on its red orbit around the Earth. And then over here, we have our sun. Now, we know that our sun does not orbit around the Earth. Okay, we're actually the ones that are doing the orbiting. But from our viewpoint here on the Earth, it looks like the sun is going around us. In fact, that's why ancient astronomers, even up to a few hundred years ago, thought that the Earth was the center of the universe because we couldn't feel ourselves moving and it looked like everything went around us. So it kind of made sense. But we now know that the Earth is the one that's actually going around the sun. But again, from our viewpoint, it looks like the sun is going around us. So the path that the sun follows in the sky, which is indicated by this blue line here, that's called the ecliptic, okay? So you'll notice that the moon's path in the sky, this red line, is tilted with respect to this blue line. So the moon and the sun don't follow the exact same paths in the sky. They follow very similar paths, but they're not exact, okay? So as a result of that, most of the time when we have, say, the moon trying to come in between the Earth and the sun, the orbit, that tilted orbit, causes the moon to either go above the sun or down below the sun in our sky. So we completely miss the moon's shadow and we don't have a solar eclipse. When the moon gets around to the opposite side of its orbit about 2 weeks later, typically that tilted orbit causes the moon to go underneath of the Earth's shadow or above the Earth's shadow. So it misses it. But what I want you to notice here is that there's two intersection points of these orbits, okay? And I've connected those with this green line. So each of those points is called a node. And then this green line is called the line of nodes. So the key here is that we have to have the sun and the moon appear in the same part of the sky, or essentially be in the same spot in the sky to have a solar eclipse, and they have to be directly opposite one another to have a lunar eclipse. So for a solar eclipse, we would basically have to have the sun at one of these nodes and the moon at that exact same node, okay? For a lunar eclipse, we would have to have the sun at one of the nodes, and we would have to have the moon at the opposite node. That way they are in a direct straight line, and they can we can have some interaction with some shadows here, okay? So, and I'm going to demonstrate this using Stellarium in just a moment here. But here's another diagram, just kind of to bring this point home. So this big circle here is the orbit of the sun around, or excuse me, the orbit of the Earth around the sun. And it sets in this square here, this big blue square. That's the plane of the Earth's orbit. Okay, so the Earth is basically moving around on this line here. Now these smaller circles, those are the orbits of the moon. But we're seeing the moon and the Earth at different positions in the Earth's orbit. Now notice over here, you can see by this square here, which represents the moon's orbital plane, you can see how the moon's orbit being tilted has brought it up above the plane of the Earth's orbit when the moon's in this position. So you see the moon has gotten too high up to where its shadow cannot fall on the Earth. So its shadow is going to go over the Earth. And then 2 weeks later, it'll pass through the plane of the Earth, and then it'll dip down below the Earth's orbital plane, and so it'll miss our shadow. But over here, now we've got that point where the moon goes into the plane of the Earth's orbit. That occurs at new moon. And the sun is also along this line of nodes. And so we basically have a perfectly straight line here, and we can have the shadow of the moon cast on the Earth, and then 2 weeks later, the moon falls into the Earth's shadow. And then we move on into our orbit, and eventually the orbit of the moon that brings it up above the plane of or below the plane of the Earth's orbit. And so we miss shadows again, okay? But then it's roughly 6 months, but it's actually about 5.5 months later, we get this position over here where we get the moon and the sun at the line of nodes, and we can have eclipses again. Okay. All righty. So one other thing I want to mention is because we don't, in order to have an eclipse, we don't have to have, especially like a lunar eclipse, we don't have to have a super perfect straight line alignment, okay? So if the moon was just ever so slightly higher here, its shadow could still hit the Earth, but it might hit the top part of the Earth. Or if it was down and below just a tiny bit, then the shadow might go along the southern hemisphere, okay? So we have some wiggle room there. We don't have to have super, super perfect alignment. We can have a little bit of a misalignment and still get some eclipses going on, especially lunar eclipses, because the shadow of the Earth is so big. So that's where I had mentioned earlier that we have an eclipse season. It's a window of about 38 days where the alignment is good enough that we'll have shadows at least skirting. Let's say the shadow of the moon skirting the Earth, or the shadow of the Earth skirting the moon. But we don't have, say, the shadow going directly across the center of the Earth or directly across the center of the moon, okay? So as long as we get the sun and the moon at the nodes within that 38-day window, then we have the possibility of an eclipse. Okay, so just to kind of give you a point of view of what this would look like again from the sun, let's go back to Stellarium. Okay, let me find my Stellarium. All righty, so again, we are looking at the moon here. In fact, I'm going to go back to the current date and time because I've moved forward quite a bit here. Okay, so let's zoom back out here. And what I'm going to do is recenter on the Earth here. Okay. Now I'm going to turn on another feature here. You're going to see a few lines. Now, oops, this horizontal line, you'll notice it goes right through the Earth there. That's just the line representing the Earth's orbit. I'm not really interested in that. If I could turn that one line off, I would, but I can't. Okay. What I'm more interested in is this other line here, which, as you see, is going right through the moon here. If I back out a little bit more, let me try to widen my screen just a bit here. There we go. All right. This is the orbit of the moon. You can see it goes way on out here, then turns on around, comes back, and comes on over here, turns around and comes back. Okay. So now let's zoom in just a little bit. I'm going to increase time. I'm going to speed up time to where it's about 2 hours every second. Okay. So now we're May 25th. Now we're getting into May 26th. This is about 5 a.m. Local time here in Nashville. And again, remember, this is the view from the sun. So the shadow of the Earth is directly behind the Earth here. Okay, the shadow of the moon is directly behind the moon. So the sun can't see our shadows at all, okay, because the Earth and the moon are blocking its view. But you'll notice that the moon's orbit is starting to bring it directly behind the Earth here. So now we're starting to see the moon disappear behind the Earth. I'm going to increase time a little bit more. See, the Earth is rotating as well. Now, let's see here, we're about this point. I think it's right around here. Oops, went a little bit too far. Let me back up just a bit. So right about here, we just reached total lunar eclipse. Okay, so we can't see it because the Earth is in the way, but if we were on the Earth right now looking at the moon, we would see the moon in that beautiful total eclipse phase. So let's continue on out. I'm going to speed up time. Now I'm going to zoom back out. We're at May 27th. I'm going to go a little bit faster. Okay. You can see some background stars going by because the Earth is moving in its orbit. Okay. And now we're at June 7th. I'm going to keep zooming in as the moon gets closer. We're at June 8th, June 9th. Zoom in a little bit more here. And then we're in June 10th. So this is about 4 a.m. on June 10th. Notice that the moon is now coming in front of the Earth. And since the shadow of the moon is directly behind the moon here, that means that its shadow is going to go across the Earth. We're going to have a solar eclipse on part of the Earth there. In fact, you can just barely see a little bit of the shading of the moon's shadow there. Okay, so this is just to show you that we had a lunar eclipse on May 26th, or will have one, but 2 weeks later, we're going to have a solar eclipse. Now, I'm going to back out. I'm going to speed up some time again. Now, this time, instead of zooming in, what I want you to do is pay attention to the Earth, or excuse me, the moon's orbit here. Notice that we're seeing the moon's orbit almost from the side, so that circle looks pretty flat. But I'm going to really speed up time here. See how the moon's orbit looks like it's tilting on around there? That's mainly because the Earth and the moon system are going around the sun. But now notice that when the moon comes on around, it's going to go down below the Earth. We're not going to have an eclipse. This is in September. And when it comes on around 2 weeks later to get into the full moon phase, it's going to get above the Earth's shadow. So we're going to have a full moon, but we're not going to have an eclipse. Okay. I'm going to go forward again. Was I doing right? Yeah. So now it looks like that orbit is getting tighter because we're getting near one of the nodes. All right, and now we zoom in one more time here. So we're on November 18th. And as you can see by the orbit, the moon's going to pass directly behind the Earth as viewed from the sun. We're going to have another lunar eclipse on November 19th. It'll start just after midnight for folks here in Nashville. So that'll be a nice lunar eclipse. And then about 2 weeks later, oops, let me back out. Speed up time again here. We are going to have, yep, you guessed it, we're going to have a solar eclipse. So now we're into December. Oop, went a little bit too far. Sorry, let me back it up. So now if we look, the moon is going to pass over Antarctica. It's going to cast a shadow on it. So if you're in Antarctica at the time, you're going to see a solar eclipse there, okay? So again, we'll typically have a lunar eclipse after we have a solar eclipse or vice versa. All right, so let's finish up with the PowerPoint here and just talk a little bit about some of the other things that you're going to see during the eclipse. So we have a couple of different types of lunar eclipses. These are, for example, the penumbral lunar eclipse. These are not very dramatic. In fact, some of them, if you didn't know they were occurring, you would probably never notice it. So this is when the one edge of the moon basically just goes through the penumbra, or that lighter shadow of the Earth. So if you were standing here on the moon, you would see a partial solar eclipse. But notice it's a very subtle darkening. So again, these aren't very dramatic. But when we have the moon going through the inner shadow, that umbra, that's when we have the very dramatic lunar eclipses. So this was a sequence of images that I took nearly 20 years ago of a lunar eclipse from here in Tennessee. This was the first image I took, then the second, then the third. And what we're seeing here, you may think, well, this looks like a penumbral lunar eclipse. It looks so much darker. Why is that? Actually, it's not. This is the umbra. This part of the moon up here was already in the penumbra. So the eclipse had progressed enough that this part of the moon down here had already passed through the penumbra and started entering the umbra, while this part up here was still in that lighter penumbra, okay? But it looks very, very dark here because this is still relatively bright compared to this part down here. And so as a result of that, I didn't want to overexpose the image. I wanted to be able to see features on the moon here. So this part of the moon looks much, much darker, and it doesn't look like it has much color. But in these images, as the moon got into the deeper part of the Earth's shadow, into that umbra, now most of the moon was very, very dark. This area up here was a little bit lighter, but now I brought up the exposure, and now you can really see the color of the moon here. So when you see a total solar eclipse, especially if it's one that's not near sunrise or sunset, where the sky is really dark, you'll notice that color is not super bright, okay? If you have it in a view in binoculars or telescope, you'll definitely notice the color, but you'll notice it's not nearly this bright. These images have been, the brightness has been increased to really show that color very well. But you can see right down here, this is the darkest, or this is the center part of that umbra, so the very darkest part. And it's right here in this view. And then a little while later, as the moon was moving this way through the shadow, we see that darker part is then moved over here. This just happened to be a decently bright star that the moon was passing by in this view here. So the total lunar eclipses are, and even the partial lunar eclipses are pretty spectacular. So the partial is where the entire moon is not within that umbra. Okay, so May's eclipse is almost a partial eclipse. It's right on the edge, but it's technically a total eclipse. In November, we will have a partial lunar eclipse, but the moon will mostly, in fact, almost all of it will be down in the umbra, so you'll get a really nice view. There's a really nice simulation that NASA put out. What would it look like if you were standing on the moon observing this? You know, why do we get that red color of the on the moon? So here we have our Earth up here, we have the lunar landscape down here, we have our sun here. So now we're going to speed up time, we're going to have the Earth passing in front of the sun here. So from my viewpoint, because I'm seeing a partial solar eclipse, that means I am now in the Earth's penumbra. Just like if I was standing on the Earth and I saw a partial solar eclipse, I would be standing in the moon's penumbra. So the lunar surface is starting to get a little bit darker now. And once we get into that deeper shadow where the sun is completely obscured, now we're in the umbra. Okay, and you notice that the lunar surface has gotten a lot darker. But as the Earth moves front a little bit more, now we're going to bring up the exposure. Okay, so now, oops, sorry, I keep doing that. All right, so now the moon's surface is bathed in this deep orangey red glow. And if we look back towards the sun, we can't see it because the Earth is in the way, but the Earth is in silhouette with a bright orange-red ring around it. So this same effect that gives us the red sunsets is happening right here. So all the colors of sunlight are coming through the Earth's atmosphere, and the redder colors get through easier than the blue colors because the blue gets scattered. But think back to that slide where I was talking about that opalescent glass and how it kind of focused the light. Earth's atmosphere does the same effect. It will bend the light some, so that some of that red light that is coming through our atmosphere gets bent and focused towards the moon to fall upon its surface. And that's what gives us our very deep red glow. So you're essentially, if you could see this from the moon, you would essentially be having a view of the sunset all around the world at once. Okay. Let me see here. So this is just kind of an illustration. It's kind of an exaggerated effect here, but you can see how the sunlight, especially the redder light, kind of gets refracted or bent by the Earth's atmosphere as the different colors pass through. But one cool thing that you can do is actually take images of the moon at various points during the eclipse and assemble them, and you can recreate. You can basically line up the edges of the Earth's shadow in each of these different views, and you can actually make out the entire Earth's shadow. So you can see just how much bigger Earth's shadow is compared to the moon, and why it takes so long for a lunar eclipse to occur, because it's got a lot of shadow to travel through. One other interesting note is, if we think back to the requirements for a lunar eclipse, remember the Earth has to come in between the moon and the sun, and it comes pretty much exactly in between, which means that as the sun is setting at full moon, the moon will just be rising, and they will be on opposite parts of the sky. Okay. Look at this shadow. You can see this shadow is very round. Some folks have asked before, well, how, there's this, there are people that are flat earthers, that believe that the Earth is flat. And, question why do we think the Earth is round? And it's a good question, because I go outside, I see a flat Earth. Doesn't matter where I go, doesn't matter how high up I go, I still see a flat Earth. So what is some evidence to show that we do have a round Earth? Well, from my viewpoint, if the Earth is flat and the sun is just setting, let's say you all are the sun and you're just setting, I'm the Earth, directly behind me just rising will be the moon, the full moon. And if we have a flat Earth, this shadow will be flat, okay? But because of the Earth's round or its spherical structure, we can actually see that roundness in the shadow itself. So if we had a flat Earth, we would actually have a flat shadow there. And so that's just one of the lines of evidence to kind of help show, why we think that the Earth is round. And it's just, I should say, it's just one of the many things that lines of evidence that we have to show that the Earth is round. So we talked a lot about the red color of the moon. But what about the, can we have something like a blue moon during an eclipse? Well, a blue moon typically refers to the second full moon of the month, because that doesn't happen every month. Typically, we have one full moon each month, but sometimes you can get a full moon at the very beginning of the month, and one gets in just under the wire before the month ends. And so we have two full moons, and again, it's typically called a blue moon. So the moon doesn't actually turn blue, but there are times where we can see a blue hue on the moon. There have been instances in which we have volcanic eruptions, or there's a lot of dust suspended in the atmosphere that preferentially scatters red light. And so the moon then takes on a bluer hue. But during a lunar eclipse, we can actually have part of the moon take on a bluer hue. And that's because of the presence of ozone in our atmosphere. So most of this red color is due to the scattering of sunlight by the densest layers of the Earth's atmosphere, which are the layers closest to the ground. Okay, we saw that in that first picture where we saw the moon rising, and as it got higher, it got brighter, and it also didn't get quite as, it wasn't quite as red as it got higher. In fact, it finally turned white. But higher up in our atmosphere, we have layers of ozone, which is really good at absorbing certain types of light, especially UV. It helps protect us from sunburn. But ozone will also absorb some of the red light. And so therefore, some of the upper layers of the Earth's atmosphere will actually scatter out some of the red light and cast a little bit of a blue hue here. And so that's what we're seeing in these two views of lunar eclipses. So up here, you notice that bluish view. Down here, you see a bluer view. I want to note, though, that if you see this with your own eyes, it won't be quite that pronounced. These have been enhanced to really bring out that color and drive the point home. But nevertheless, it is an effect of our atmosphere. So to finish up, what are some details about these upcoming eclipses? So in a little less than 2 full days, we will have a lunar eclipse. If you happen to be in the western part of the United States, you'll have a much better view than we have here in Tennessee. In fact, just as we start to get into almost this phase here of the lunar eclipse for here in Nashville, we will actually see the moon setting. In fact, we can simulate that as well. But notice that the times here are Central Daylight Time. So we're observing daylight savings time. So you can subtract or add however many hours that you need if you happen to be, west of here. So if you're over in California in the Southwest, if you're in Hawaii, you'll get a great view of this. But here in Nashville, we're not going to get quite a super good view, and it'll really require a good clear southwestern horizon in order to be able to see this. So in fact, let's go ahead and simulate that. Let me go back to Stellarium, and then I'll have one more slide, and we'll do some Q&A here. So I'm going to zoom back out here. In fact, I'm going to go back to, let me go back to my default location, which is right here on the Earth, if it's going to do it. I think it will. Well, let me just go. Let's see. Now I need to zoom out. Give me 1 second here to get this set up. Okay. So here's our current view if we were surrounded by a big ocean. But now let's go forward 1 day. And then we're going to go over to, oops. Okay. So this is tomorrow night. And the sun is just set. We've got our moon coming up here. I'm going to zoom in right quick. So we get a little bit of a yellowish view from our atmosphere here. So now let's go forward an hour at a time. So this is 8 o'clock tomorrow night, 9 o'clock, 10 o'clock, 11, 12, 1, 2, 3, 4. Now we're at 5 o'clock. The penumbra has already started to move over the moon here. Now we're starting to see a little bit of that umbra coming in. We're starting to see a little bit of that red color. Now, because we're not going to see much of that umbra, you probably won't see much of that red, but you'll definitely notice as the moon is setting that it's going to definitely have one edge that appears darker. Now I'm just going to go forward a little bit at a time. So this is 5 a.m. That's 5:18. Now we're starting to get really close to the horizon. We're starting to get the sun coming up, which is going to make it harder to see some of the effects of the eclipse. So now we are at about 2 degrees above the horizon. So basically the horizon's just off the edge of the field of view here. In fact, I can go forward a little bit more. You may notice that the moon appears to be squashed, and that's because of the bending effects of our atmosphere. So if you had a perfectly clear horizon here in Nashville, you'd be able to see some of that eclipse, you'd be able to see some of that umbra. In fact, let me turn off the atmosphere just to, kind of show you where we would be at. But because of that atmosphere, it's going to make it much, much harder because the atmosphere is glowing brighter as the sun is getting higher, okay? Now, in November, we will have one other eclipse. So now let me, I'm going to back this up just a little bit. Let me change my time. And we're going to go to November 19th. Oops, too far. All right. So this is just before midnight on November 19th here in Nashville. Actually, I need to go back one day. Sorry. Okay. So now I'm going to zoom in on the moon here. Okay. Steady our view there. So we're getting just close to midnight. Now we just passed midnight, and I don't know if you can see it, but there's a very light shading that's starting to come down through here. All right, so the moon has now completely entered the Earth's penumbra. That's right around 1:15 in the morning. And I'm going to go faster in time here. So now we're at 2 a.m., about 3 a.m. So you notice that this part of the moon doesn't get quite as much umbra. So this is why it's a partial eclipse, because this part's still in the penumbra. But you'll definitely be able to see this reddish color here. Then, so we're at 3 a.m., we're at 5 a.m., and now the sun is starting to rise up, and we basically have ended our eclipse. So if you're in Nashville, then you're going to, let me go back to my last slide here. You're going to be able to get a much better view of the November eclipse. You'll have to stay up late to watch it, but here's a map from NASA that basically shows the US, and you can see that almost the entire continental United States, except for parts of Florida and parts of the East Coast, get to see the entire eclipse from the very start to the very finish. But folks in Florida and along the East Coast, you'll still get to see about like 95% of the eclipse. So it'll still be a great view for you. Folks over in most of Africa won't be able to see it at all. But some folks will be able to see parts of the eclipse, just like we'll be able to see parts of this eclipse in 2 days. So, all right, well, with that, we are at about 8:04, and that was actually my last slide there. So let's look at getting some questions here, and Helen has sent me a number of them. So let me take a look here and see what we've got here. All right, so our first question is, why do the first and third quarter look different? So the relationship of the sun and the moon seem identical. It's a very good question. So let me go back to, let me find that slide. Yes, so what you're going to notice is that so we start typically, when we talk about moon phases, we typically start with the new moon phase, okay? That's just by convention. So as the moon begins to move around the Earth, we're going to start to see the right side of the moon become illuminated, okay? Because when we're at this phase here, which is represented right here, we're starting to see just a tad bit of this part of the illuminated moon here, okay? Now, as we move on around, now the right half of the moon is completely illuminated. And as we keep on going, the moon starts filling in more and more from the right side towards the left side, okay? And we finally get to full moon and we've completed our first set of phases. So as we're filling in from the right side, we are in our waxing phases. So the amount of illumination on the moon is increasing all the time until we get to full moon. Now, after that, we start decreasing from the left side and we start going through our waning phases. So one thing that you'll notice is that for the first quarter, we have the right side of the moon is visible. For the third quarter, the left side of the moon is visible. And so it really, this is where you kind of have to, it's hard to show just a picture here and actually try to explain this different perspective view. But one thing that will really drive the point home, and we can try it with Stellarium in a moment if we have some time, is set up this moon phase experiment in your living room. You know, get you a lamp, set it in the middle of the room, take the shade off, and go get you like an apple or an orange or something like that. Oranges are great. Tennis balls or ping pong balls are great. Basketballs are fine, whatever. But have whatever object you chose, make that your moon. And your head, have that be the Earth. Basically have the moon, your basketball or your apple or whatever, go through the different phases. So again, if you guys are the sun, then I could hold the basketball up in front of me and this would be my new moon phase. And then as I stand here and I kind of rotate, I move the moon over to this side to my first quarter phase, and then to my waxing crescent and my first quarter phase. Go through all the different phases and you can see how the phase will change as you change your position. So it really has to do with the angle between the moon and the sun. So when I'm going to my first quarter phase, I have the moon in front of me, but the sun is over to my right side. But then as I move on around, I completely rotate around so that I go through my full phase, and then I get to my third quarter phase. Now the sun is over to my left. So I have the different side of my moon being illuminated. So definitely try it out, because then you can see, you can even put the angle of the moon's tilt in there, the tilt of its orbit, to see how you can miss the sun and not have eclipses and things like that. I'd highly recommend it because it really drives the point home if you can actually do it with your own, see it with your own eyes and try it out. So let's see here. Do we have a formula to calculate the lunar and solar eclipse dates? Yes, so there are actually a number of formulas that will go into that, because you have to take into account a lot of different variables. You have to take into account where the Earth is in its orbit, where the moon is in its orbit. You have to determine exactly how long it takes the moon to rotate around the Earth. Remember that line of nodes or I'm sorry, not the line of nodes, but remember how I was talking about how the moon has an elliptical orbit, how it's, farther at some times, closer at other times. Well, that oval shape, that ellipse shape of that orbit, that long part of the orbit, that's called the long axis. That long axis doesn't stay pointed in the same direction all the time. Over a period of a little over 18 years, that orbit gradually rotates around, and that affects the eclipse timings as well and where the moon is going to be in its orbit. So there's lots of different variables. But having said that, ancient astronomers actually started observing the sky. They were excellent observers. They didn't have telescopes, but they had good dark skies. And when it got dark at night, they didn't have much else to do other than to see what was up in the sky. They didn't have movies to go to or anything like that. So they were excellent observers, and they made very detailed notes of where objects appeared in the sky, and they started to see patterns and were actually able to start predicting eclipses centuries before the first computers were able to do that. So there's a lot of history in that, which could be an entirely separate talk. But suffice it to say, there's a lot that goes into it, but we have very very accurate formulas that can predict eclipses down to, within a few seconds of when they should start, when they should end, what they should look like for different locations on the Earth. So there's a lot that goes into it. Let's see. So why does the size of the moon seem to change when there are objects on Earth between our eyes and the moon? So that is a very good question as well. That is what a lot of people refer to as the large moon illusion. So if you've got a good clear horizon and you see that moon just rising, and I've observed this many times, a lot of times you'll look at that and you'll say, you would swear up and down that the moon is like 10 times its actual size. And it does, it looks absolutely huge. But that is simply an illusion. A lot of people, I should say a lot of people, but the leading theory is that when the moon is high up in the sky, we really don't have objects to compare it to in size, but when it's down near the horizon, we have trees, we have buildings, we have things that we can see that we know are very far away, and as we get closer or farther from those things change size. But it doesn't matter how we change our distance from the moon, we really don't see a change to it. So the leading theory is that it's simply just it's simply just an illusion. The next time you see that, you can do something to convince yourself that it's an illusion. So if you take let me see if I can back up here. So if you take your finger and you hold it out at arm's length, okay, so you see that huge moon rising, hold your finger out at arm's length, like your index finger, close one eye and put your fingernail right next to the moon and make a mental note of how big that moon appears. In fact, if you're at home watching this right now, go ahead and do that. Just see how big your fingernail looks, okay? Believe it or not, and I'm talking about my index finger here, believe it or not, your fingernail is actually wider than the full moon, okay? And I know I've seen it where it looks like it's huge, but believe it or not, next time you see it when it looks huge, do that same thing and you'll see that the moon is actually smaller than your fingernail. Try to make a mental note of just how big it is. And then about 6 hours later, when the moon's high up in the sky and it looks much smaller, do the same thing. And you're going to note that the moon looks exactly the same size with respect to your fingernail as it did earlier, okay? So if we have a little bit of time, there's one other thing I'd like to talk about regarding that. When you see the moon and it's rising and it looks bigger, believe it or not, if you actually measured it, I mean, had a camera on a telescope to where you could go into software and you can measure it like by how many pixels wide it is. If you take a picture of the moon when it's huge and it's just rising, and then take a picture of the moon when it's higher up, you'll find that the moon, when it was just rising, is actually a little bit smaller. Now, why is that? So I'm going to go back to my view here of the moon phases. So when we are, so let's say, okay, here's our full moon over here. When the moon is just rising, remember that's when the sun is just setting and the full moon is just rising, we are essentially right on the day-night side of the Earth. So we're basically right here. And then over a course of a few hours, the Earth is going to rotate around and we're going to rotate with it on its surface. And eventually around midnight, we're going to be about right here. So when we see the moon, when we're standing right here, that's when we see it at the horizon and it looks enormous. Note the distance between me and the moon right there, okay? Now again, this isn't to scale, but the concept works. Now, 6 hours later, when the Earth has rotated around and rotated me around to where I'm right here, now I'm closer to the moon. Because I'm closer, it's physically going to appear larger in the sky. So that one, it's a much more subtle effect. And the reason that it appears larger is when it's higher up is because we have rotated around so that we are about 4,000 miles or so closer to the moon. So it's a small amount, but it can have a measurable effect. Let's see. Is there a way to show the lunar eclipse from Nashville using the software? Yes, we got that one. Let's see. Millions of years, or in millions of years, will there be a different number of eclipses? Or are the Earth, Moon, and Sun fixed enough that these positions will be the same? One thing we didn't really talk about is that the moon is gradually spiraling away from the Earth. So the Earth and the moon both have gravity. They're pulling on one another. And because we are not uniform spheres of uniform density, that means that gravity is going to tug on the irregularities of the Earth. So the moon's gravity is going to tug on those irregularities of the Earth. The Earth is going to tug on the gravitation or on the irregularities of the moon. In fact, the Earth has done so much because it's got a stronger gravity that is why the moon keeps one side facing us. Because as the moon was rotating, we kept pulling on those little irregularities, which kept slowing the rotation of the moon down until finally it kept one side facing us. We basically stopped its rotation from our viewpoint. Now, from the sun's viewpoint, we see that the moon is rotating, and that's because it's tidally locked. But the moon is doing the same thing to the Earth. It's very gradually slowing down our rotation. If I recall correctly, it's about 1 second every 10,000 years, which doesn't seem like much, but it is a measurable effect. A consequence of that is that because we're slowing down, that means our rotational energy is decreasing. Remember the famous, what's not saying, but one of the basic principles of science is that energy cannot be created nor destroyed. It just changes form or goes somewhere. So because the Earth is slowing down, that means its rotational energy is going somewhere. It's being transferred to the moon, which means the moon is getting into a larger and larger orbit. How much farther away is it getting every year? Oh, about 2-3 centimeters or so. So it's not much, but over time, that will have an effect. Eventually, the moon will get far enough from the Earth, and as it gets farther away, it appears smaller. Eventually, we'll get far enough away that it will never be able to be large enough to completely cover the sun again for a total solar eclipse. So go far enough in the future, and I forget how many years that is. It's a while, but we will no longer have total solar eclipses. We'll still have partials and these solar eclipses called annulars, where the sun looks like a ring, but we won't have total eclipses. We'll still be able to have lunar eclipses, but because the moon is as these objects, or as the moon is getting farther and farther away from us, it's going to require a much more precise alignment to get it to go through our shadow. So those eclipse windows can shrink down, and as the moon gets farther away, the time between full moon and full moon is going to increase as well. And so it instead of every 5.5 months, it might be every 5.5 years that we might have an eclipse. So things are constantly changing over time, but it's not going to be anything dramatic in our lifetimes, or several lifetimes. Let's see here. Is it true that eclipses influence human minds? If so, why? So there's no scientific evidence to say that, yes, when we have an eclipse, it's going to have an effect. Like if I put somebody in a room and lock them in there, they had no idea what phase the moon was in, they had no windows or anything, they would not be able to tell that an eclipse is going on. Now there are, obviously there are cultures that have traditions and other beliefs that are centered around eclipses, all types of eclipses, and other things going on in the sky. So that might have a very significant impact on them for their culture. There's I've heard many times that if there's a lot of goings on in a city, like a lot of crime on a certain night, or something crazy happens, like a certain crazy crime happens, that people say, oh, it must have been a full moon. You might think that you feel different for a full moon, but you're really not. Okay, so that's about all that I can say on that one. I think that is all the questions that I see, unless there were a few others that came in, but I don't believe so. Well, we're at 8:20 anyway, so we're over our hour, but thank you all for joining me tonight. I always enjoy talking about the moon because it is, it's something that we all experience in our lives. No matter where we are on the earth, we're going to be able to see the moon. And, it's always nice to be able to, to educate people about these things that we're seeing so that they have a better understanding of what's actually going on. So it's like I said at the beginning of the talk, if there was one thing that I want my intro astronomy students to learn from the courses that I teach, is that what causes the phases of the moon. Another one would be like, what causes the seasons? Or why do we have eclipses? Because these are things that we all see and encounter in our lives. So I hope that if you had any misconceptions, I hope we got those cleared up. I hope that everyone learned a little something tonight. And thank you again for joining us. As I told our virtual star party folks, even when we do reopen, whenever that ends up being, we are going to, especially for things like the Meet the Astronomer lectures, we're going to try to continue having a virtual component for that. For folks that maybe can't make it, or maybe you're located well far away from the observatory, we still want to be able to reach out to you all. And we really appreciate all of you all joining us for these events, because the observatory is a big part of our mission is education and public outreach. And so we love being able to do this. So again, thank you all for joining us, and I look forward to seeing you next time. Be sure to check out our homepage and our social media for any upcoming events or changes in our schedule. So thanks again, and hope you all have a great night. Hope you get to see the eclipse a little bit. And if you don't get to see this one, we've got the one in November to check out. So we'll be talking about that more once we get near that time. So everybody have a great night, and be safe out there.